So here's another example of optimization. This one's a little bit challenging, which is why I'm showing it to you here. We've got a capsule. Basically, it's a cylinder plus two hemispheres. So a half circle, a cylinder, another half circle. It makes a nice little capsule. I don't know whether this is to hold something important. I don't know whether this is a giant pill for someone. Whatever its use could be, it needs to have a volume of 14 cubic centimeters. Now, what we want to do is figure out what is the radius that's going to minimize the surface area. I wrote this problem as short and sweet as possible. What is our primary equation? What would we be trying to minimize? If you said we were trying to minimize the surface area, you are correct, because it says minimize the surface area. And if you didn't know this equation, it's the circumference times the height for the cylinder. And then two semicircles, we're just trying to get the outside. That's like the equivalent of the surface area of one whole circle. So here it is. Now my problem is, on the left side we have one variable. On the right side we have two, height and radius. We need another auxiliary equation. That would help us. And what's the only information that we were given? Come up with an auxiliary equation that will help us to rewrite the surface area one. If you said the volume of the cylinder plus the volume of the sphere, you are correct. And we can even plug in this number, which has to be 14. So I'm using my auxiliary equation. I'm going to rewrite it in terms of h and plug it in here to eliminate one of the variables. Here's how that might look. I've solved for h. Plug that back into the surface area now. And now I don't like my primary equation anymore. It's too ugly. I don't like it. Sorry. But that's what I'm supposed to do. I'm using my auxiliary, plugging in my primary. I'm down to just one variable on each side, radius and surface area. Thank God it simplifies a little bit. And now, is there a realistic domain? Well, I know my radius shouldn't be smaller than 0. I don't know what its maximum is. I could figure it out, but it's going to be realistic small positive numbers. Now I'm going to take the derivative and find those critical values. Well, that derivative is a bit discouraging except for one thing. Optimization problems, you get to use a calculator. How cool is that? So when you're trying to say, what's going to make this derivative equal 0? Obviously, the radius could be 0, but that's not going to be very large. I don't think that'll give us our best answer. However, graphing this on your calculator, you can find out what makes this derivative 0. Well, that's if r is about 1.495 centimeters. It's an interesting answer because not only does that give you the minimum surface area for that radius and the volume of 14 cubic centimeters, it also, if you plug it back in, will give you a height that is 0. So, not surprisingly, if you want to minimize the surface area, a sphere gives you the best chance. An actual, cylinder with a hemisphere on each side, a capsule, is not your most efficient one if you're trying to save on the materials on the outside of this capsule. So that's how you can do that problem. So that last example was a bit longer. They can be short and sweet, and there's all kinds of different equations that could pop up, especially those involving business, areas, or volumes. But here's one where the range of a fired projectile can be given by the original velocity squared times sine of 2 theta divided by gravity. This is a much simpler problem because we're given a primary equation that I've probably never seen before. I look on the right-hand side and there is only one variable there. The original velocity would depend on whatever you're firing from, but it will be a constant. It won't change. Gravity also will not change. So you're left with no auxiliary equations, no substitution. A reasonable domain is probably between 0 and 45 degrees so that you're not shooting past straight up and down. And you're left with the coefficient times the derivative of the sine function there. Of course, this function's only going to equal 0 if cosine does, and cosine will equal 0 at a 45-degree angle. Common sense.